Hello, this is Professor Keen. I'm talking about Pascal's principle. This is from a student's guide, volume 2, chapter 14. Here, I'm giving you a short reminder of what we talked about in the last lecture. The idea is that a box full of fluid can be treated as a machine that obeys Pascal's principle. Specifically, and this is what Pascal talked about in this section, in section 14.2.2.1, where he says, in a vessel full of water, closed on all sides, if it has two openings, one 100 times larger than the other, with a piston carefully fitted to each, a man pressing the small piston will match the strength of 100 men pressing the piston in the 100-fold greater opening, and will overmaster 99. So that is depicted here, where we've got this chamber full of fluid. If you have a force being applied to the small piston with an area A in, there will be an output force here that is exerted on something over here, and this one has area A out, and the ratio of the output to the input force is equal to the ratio of the areas of those two. How did Pascal arrive at this, the formula in the box called Pascal's principle? Well, he derived it from the idea that for any machine, the work that you put into it is equal to the work that you get out of it. The nice thing is that, so this is what Pascal describes at the bottom of page 180 over here. The nice thing is that he arrives at Pascal's principle, this right here, in another way. So if you don't like the previous proof using the idea that the work out equals work in, he's going to derive it in a different way on the next page. So on page 181, he derives it in a slightly different way. So what I'd like to do is go through that proof of Pascal's principle. So let me draw a line right here. And we're going to do a second proof of Pascal's principle. And just to be clear, what do we mean by Pascal's principle? It's this formula right here. Okay? How do we do the second proof? How does Pascal do a second proof of what is now known as Pascal's principle? Well, we need to have a little bit of background knowledge. Just like before, we needed to have a background on the idea of what we mean by work, and that work out equals work in. Here we need a little background knowledge. And the first piece of background knowledge we need to have is the idea of equilibrium for an object. What do we mean when we say an object is in equilibrium? Well, if we have, for instance, a wooden block and you apply a force to this side, what's going to happen to it is it's going to begin to accelerate toward the left. There's an unbalanced force. But if we apply the exact same force to the left side, then those forces are going to be balancing each other. It's going to be in equilibrium. And if that block was sitting on the table, let's say this was a table, and you apply the same force from the right toward the left and from the left toward the right, this is going to be in equilibrium. It's not going to begin moving. Okay? So this applies not only to wooden blocks, but it also applies to blobs of fluid. So let's suppose I have some blob of fluid right here. Maybe it's a blob of jello, maybe a funny fluid like that. If I apply a force like this, it will make it accelerate leftward. If I apply a force on the left side, I can balance that out so that it does not move to the left. Now it's not going to move left or right. But if this is a deformable fluid, you might imagine it's going to squish downward or squish upward. So I'm going to need to apply the same force to the top and the bottom. And if I do this for a blob of fluid, then it is not going to move upward, downward, left, right. It's not going to deform. It's going to be, again, in equilibrium. Okay, so that's just an extra complication we need to think about for deformable or pieces of fluid. Okay, so for each object like this to be not moving or in equilibrium, it must be equally pressed from all sides. Here's one other piece of information that we need to have. If we have two adjacent blocks right next to each other, and let's suppose we try to push block A toward the right, it's going to make contact with block B on the right. And so what's going to happen is block A is going to be pushing on block B, and block B in turn is going to be pushing back on block A. So here's a fundamental piece of information that we're going to need to keep in mind, that if blocks A and B are in contact, then block A pushes on B with the same force that B pushes back on A. Back on A. This is a very important law that will later on be referred to as Newton's third law. So this later on comes to be known as Newton's third law of motion. Now, Newton did not write his Principia, where he describes this, until 1687, and Pascal is writing much earlier than that, so I think it's very interesting that Pascal employs what comes to be known as Newton's third law of motion without actually, this is quite some time before the time of Newton. In any case, whenever you have two interacting objects, object A pushes on B, B is going to push back on A with the exact same force. Okay, so these are two pieces of information that we need to keep in mind, 1 and 2, when we're looking at the second proof of Pascal's principle. Now, here we go. Here's the idea. Let's suppose that we have a chamber, once again, full of fluid, and we have two openings in this chamber of fluid, and one opening is much larger than the other. And I'm going to put a piston in this one, a movable piston, and another movable piston in this one. Okay? And I want you to imagine, once again, that there is a force you're applying on this side, an input force. And we already know that there's going to be some, this force applied here is going to push on this fluid, the fluid's going to push on this piston, and we're going to get an output force. And the question is, what is the relationship between the input force and the output force? Well, here's the second way that Pascal describes it. He says, let's suppose that this input piston has an area, an input area of, let's say, 1 square inch. So if that's the case, let's just imagine this fluid, there's a 1 cubic inch little volume of fluid that's right next to this. Okay? And so that force is going to be pushing on that little piece of fluid. Now, for that piece of fluid to be in equilibrium, the piece of fluid that's right next to it is going to have to be pushing back on it with the exact same force. Okay? So if this block of fluid, block A, is pushing on block B is pushing back on block A with the exact same force. Right? And now we can think of a chain of these little 1 cubic inch parcels of fluid. We can imagine little 1 cubic inch parcels of fluid on all sides of this one. And for this one to not be moving, then each of the little parcels next to it has to be pushing on it from the left, from the right, top and bottom. So in other words, for this whole situation to be in equilibrium, we can imagine all these little, I'm going to just imagine all these little parcels of fluid, they're all going to have to be pushing on each other with the same force in order for this whole situation to be in equilibrium. I could do this all the way over to this side, and now the question is, how many little parcels of fluid are in contact with this piston? Let's suppose this piston is just big enough that 1, 2, 3, 4, 5. Let's say this one has an output area is 5 square inches. That means there are 5 little 1 cubic inch parcels of fluid that are all pushing on this output piston. They're all pushing on each other, and they're all pushing over here on that. Now, see what's happening here is, for this whole situation to be in equilibrium, the input force has to be related to the output force in a ratio of 1 to 5. That is, the force that's exerted on the output piston is to the force that's being applied to the input piston in the same ratio as the output area is to the input area, by virtue of the fact that each of these 1 cubic inch parcels of fluid must be pushing on each other with the exact same force for the whole thing to be in equilibrium. And since there are 5 little 1 cubic inch parcels of fluid pushing on this piston, each one with a force of whatever force you had here, then, like, so for example, if there's a 1 pound force pushing over here, each of these little parcels of fluid must be pushing with a 1 pound force on the output side, and so the force out would be equal to whatever the force in was times A out over A in, and in our case we'd have 1 pound right here, and then the ratio of the output area 5 to 1, and so the output force would be 5 pounds. So we've arrived at the exact same law, that is Pascal's principle, but now instead of using the concept of work, input work equal output work, we're using these ideas of all these little parcels of fluid being in equilibrium with each other and pushing on each other with equal and opposite forces, and then pushing on this wall over here, each one with the same force. And so that gives an output force to an input force of 5 pounds. And this is Newton's second proof of what came to be known as Pascal's principle.